Welcome to my talk. This is going to be a long talk, to be honest. I did a test run today. It was like 45 minutes, as we discussed. And I want to tell you something about our STX Accelerator we are developing and the corresponding LLVM-based compiler. First thing I want to tell you is what is the stencil and tensor accelerator we are developing. Then something about programming models for accelerators in general. Then I'm going to talk about the STX's hardware architecture and the necessary software infrastructure to use it. And before I'm going into some details at the end, I'm talking about LLVM's OpenMP offloading implementation, how this works at runtime and at compile time. And then I want to show you some selected challenges we were facing during the project, namely implement OpenMP offloading in LLVM for a specialized instruction set processor, and implementing nested OpenMP offloading, where you can have nested OpenMP target regions and offload from a host to a device level 1 and then again to a second device level. Okay, so let's start with the stencil and tensor accelerator. First, about the Fraunhofer Society. The Fraunhofer Gesellschaft, is a very large leading applied research organization. We have currently 76 institutes and over 30,000 employees in Germany. And the goal is to get research into practice to support society. And we are working in in a multitude of scientific domains, engineering, biology, electronics, and so on. And the Fraunhofer Institute for Industrial Mathematics, ITWM in Kaiserslautern, that's where I'm working. It applies the approach of Fraunhofer to bring research into practice in the context of mathematics. And as you can see, at the moment we have over 200 scientific people working, lots of PhD students doing projects, so it's a pretty large institute already and interesting projects going on there. There are several departments at Fraunhofer ITWM, and I'm working for the Competence Center High Performance Computing, CCHPC. And we are having activities in quantum computing, seismic imaging, data analysis, and also energy efficient high performance computing. And that's the context of the STX Accelerator project. So the CCHPC is developing the stencil and tensor accelerator, or shortly STX. And the purpose of this hardware accelerator, let's call it a bit simplified a processor, is to perform stencil pattern floating point computations on multi-dimensional data volumes. I will talk a bit later what this actually means and show you some examples. And the purpose of this STX accelerator is to do this in an energy efficient way. We developed this processor in a hardware-software co-design approach, where we developed the hardware and the corresponding compiler and runtime libraries based on LLVM together, and they evolve together. And the central goal, or a central goal we have, is to achieve ease of programmability for users. I will also cover some details of this later. So why is energy efficiency in supercomputing important? Well, if you have a look at the top 500 supercomputers list, which maybe in this context all of you might know, at the fourth rank here, the supercomputer Fugaku has a power consumption of 30 megawatts. I looked up the data and I found out this is the electricity consumption of 40,000 people in Germany, and not only the households, but Germany scaled down to 40,000 people. It's everything, including industry. So that's pretty a lot of electricity. And on the one hand, this of course generates very high operational cost, because electricity is not very cheap nowadays. It also has an ecological impact you do not want to have. And we are also running in some kind of energy barrier with these machines, because you cannot arbitrarily increase the number of processors anymore, because you cannot create a computer that consumes like a gigawatt of electricity. So energy efficiency in supercomputing is important, and that's what we are trying to do with our STX accelerator. So why is our accelerator energy efficient? Let's consider general purpose processors versus specialized processors. On the right-hand side, you see an example of x86 assembly language. That's a general purpose architecture. And you have lots of different instructions there, like data movements, doing arithmetics, comparing things, doing logic, branching, and so on. And this tends to have a complex implementation because, for example, you need a good branch prediction for high performance, and that takes a lot of transistors which consume energy. And yeah, in tendons, this kind of architecture, general purpose processors, have a higher energy consumption. On the other hand, the STX contains a specialized processor for stencil pattern, floating point computations on multi-dimensional data volumes. And what do I mean with that? Well, let's consider this example code here. This is called an isotropic wave equation. Its purpose is to compute the propagation of pressure in a three-dimensional wave field, as you, for example, need to do in climate models. I'm not a domain expert on this, to be honest, but I've been told that this kind of kernels are computed in this research area. So what you have here is you can see those loops for z values, y values, and x values, and those are indices in a three-dimensional data volume. So pressure, that's a field of 3 dimensions, and the elements are floating point values. And what you do in this kind of mathematical kernel is you iterate over all center points in the data volume. And for the given center point identified by z, y, and x, you do computations around that center point. So you load data from the pressure wave field based on the center point z, y, x, but also a bit, you increase z by r or decrease z by r, and you have a star-shaped stencil from which you read around the current center point, floating point values, and you do computations, arithmetics, and then you write back the data. So that's a typical example of stencil pattern computations. And that's pretty much what the stencil and tensor accelerator is intended for. So you want to do this kind of computations in a highly performant way, and do it in an energy efficient way. Okay, and how do we achieve this? Well, the accelerator contains a stencil processing unit. That's how we call it. It is tailored for stencil pattern computations, and that's the special purpose processor that's tailored to do exactly this kind of computations. And it's energy efficient because we have hardware support for things you need to do when you compute kernels like the one I've shown you. It has, for example, hardware support for iterating over center points in a multi-dimensional data volume, for example, for enumerating all the index combinations. You need to do address calculations in the data volume because the data will be like made flat in memory, and you need to index all the elements correctly. And in combination to this hardware support, we also have a dedicated instruction set architecture, which has specialized instructions to program for this architecture. And something I will mention later in the talk is, you can remember that, it's the ISA, the instruction set architecture, has no branching instructions. And that's causing some challenges if you want to write a backend for this in LLVM. Okay, and the goal of the STX accelerator is to be competitive in terms of compute power with other accelerators like GPUs, but have advantages in terms of energy efficiency for the class of stencil pattern kernels. And as I said, an important aspect is to have good user acceptance, ease of programmability. So let's talk a bit about programming models for accelerators. There are different programming models for programming for such accelerators to offload computations from some kind of host to an accelerator. And typically they involve explicit management of the accelerator and the computations. Let's consider, for example, the SQL language. This is an example from Intel's one API samples. I don't want to go into the details here, and also I'm not a SQL expert, to be honest. But as you can see, to program in the SQL language, you need to do things like manage buffers that contain data. You need to manage work queues that contain like work items to be processed. You need to specify how to access that data in the buffers, and you have to put your actual kernel, it's down here, sum of I is A of I plus B of I. That's the actual computation. And that's a lot of code around it, to be honest. You need to manage to get this working. So if you program in this kind of language, I've put it in orange here, you think about the accelerator a lot. Whereas ideally, you would want to think about solving the domain problem. And the OpenMP offloading approach is a bit different, and it's more like think about the domain problem, because it's an approach that follows like almost plain code single source file approach. What you have here is admittedly a more simple computation. You start in a main function on the host. You set some integer variable, my value, to 1 and print it out. And then using the compiler directive pragma-omp target, you offload this the following region, code region, to the accelerator and execute it on an accelerator device. But as you can see, there's this, again, this variable, my value. You can set it on the accelerator, and if you return to the host, this code will print out that in the end on the host, the variable is also set to 2, because the map clause at the pragma-omp target says I want to map it to and from the device. And yeah, that's the way this code is created. And that's, I think, much more easy to program, like compared to an explicit model. And yeah, in this programming model, you tend to think more about the domain problem than about the hardware. So while explicit programming models like SQL are good for maximum performance via fine-tuning, because you have total control over data movement, for example, it's maybe hard to program for non-experts, like, for example, physicists, which do physical simulations in research projects. These guys want to think about their physical simulations and not about programming for an accelerator. And that's why OpenMP offloading as a programming model is maybe much easier for people like this. And the goal with STX is we want to provide ease of programmability for non-experts and achieve close to maximum performance. But of course, allow experts to fine-tune by mechanisms we have to provide. Yeah, and that's the reasoning why we chose OpenMP offloading for the STX Accelerator, because a main goal is ease of programmability, besides energy efficiency, of course. Okay, so let's talk a bit about the STX's hardware architecture and the software infrastructure. On the right-hand side, you see a diagram of our accelerator. What you can see is we have a host processor. It's a RISC-V 64 core. You have some host memory, which is shared. And then you have lots of clusters. And each compute cluster contains several RISC-V 32 cores. One core is DMA capable and can move data from host memory to a software managed scratchpad memory, and can move it back also, of course. And then you have further RISC-V 32 cores, and those are management cores which control second level offloads in the end to our stencil processing unit. And the stencil processing unit is the processor which is tailored for stencil pattern computations. So the programming model in the end is, on the left-hand side, I have made a condensed example. You start on RISC-V 64, and you prepare your data volumes in host RAM. Those are the floating point data volumes you want to do computations on. And then you offload to many clusters in parallel. For example, via the directive pragma-omp target teams, and you hand over the number of clusters you want to use, and this offloads to all those clusters in parallel. Those are those arrows here, which denote OpenMP offloads. Okay, and then while you are on a cluster, what you can do is you can, for example, determine your cluster's current index based on this index, you can determine which tile of the overall host data volume you want to do computations on. You move data to the scratchpad memory via the DMA core, and then you offload the actual computations to the SPU, which does it energy efficiently. Then you move data back, and then you're finished in the end. So that's the basic idea of the hardware architecture and the programming model we want to have in the end. And as you can see, we have pragma OMP target, pragma OMP target 2 times. So that's what we call nested or 2-level OpenMP offloading. And an interesting thing is this is currently not yet officially contained in the OpenMP specification, and also not in upstream LLVM project, I think. And that's why we needed to implement it ourselves. There's a question? Maybe one short question, yeah? Yeah. Yeah. Yeah, the problem here, I think, is that at the moment, I mean, if you want to really also have fine control over data movement, which is necessary to have good performance, I think there are no constructs in OpenMP that allow you to data map, for example, structured multidimensional data volumes in the form of tiles to scratchpad memories of accelerators. So that's why you need, at least at the moment, to have control at the first offload level via an explicit code you can write as a programmer to control data movement to the scratchpad memory and then do the computations in a second level offload. But of course, this may be changed in the future. We are working on ideas to have a single level offload in the end by doing some kind of automatic data mapping, for example, or maybe change the hardware architecture also by integrating the stencil processing unit more with as an extension of the RISC-V instruction set architecture. But that's at least our current development state, motivated by considerations like I mentioned. Okay. Okay, so what we did in the project was we developed SPU LLVM, as we called it. It's an LLVM-based compiler and runtime libraries. And what you can do is compile and execute C++ OpenMP offloading applications for the STX Accelerator. Currently, we are based on upstream LLVM as of May last year, LLVM 17. And due to the special architecture I've shown you, there were really lots of challenges in the project we were facing. For example, we have this specialized instruction set architecture processor. And to support this kind of architecture in LLVM's software architecture, which is, I think, made for general purpose processors, it's not really trivial to do it. And then we have this 2-level nested OpenMP offloading. And another thing is also, maybe let's jump back one time to this slide here. The clusters to which we offload from the host are bare metal systems. There's no real operating system. Not minimal, but reduced C library or C++ library support, no dynamic linking and so on. So yeah, we also had to implement lots of technical things to make OpenMP offloading from a bare metal host system possible with completely static executables. Because in upstream, I don't know the current development state, to be honest, but at least until recently, you need to have dynamic linking because the plugins are loaded dynamically. Yeah. So what we had to implement was a way of creating fully static executables that can do OpenMP offloading. Okay. What are the use cases for the final users? Well, as I said, the scientists which will be using our software infrastructure will program scientific applications and compile them targeting the STX Accelerator for commercially available accelerator boards that are going to be produced. And in their use case, they will offload from RISC-V 64 Linux to bare metal STX RISC-V 32 clusters and then to the stencil processing units. But of course, for us developers, for infrastructure development, debugging, also training, there are also is a multitude of other use cases which we support. For example, simply offload from your x86 Linux system to a software simulated SPU to try out developed features in our LLVM compiler or in the runtime library. And we also, besides a software simulator we developed for the SPU, we can also offload to a very-related SPU. Very-related means there's a software called Verilator, which is able to do a simulation of a hardware defined by a register transfer logic. So we can offload to, let's say, a hardware simulation also of the processor, which is ideally practically the same as the actual hardware. Then we can do nested offloading from x86 to x86 to the same machine, and then to the SPU as above. Of course, for developing and debugging the nested offloading. And then what we can also do, for example, is offload from the RISC-V 32 cores in an STX cluster to the SPUs for a single cluster and execute this in QuestaSim, which is again a hardware simulation tool, and it simulates on a register transfer logic level what the gates are doing in the hardware. So this is practically the same as the real chip. We also have an FPGA setup where you can boot Linux on your RISC-V 64 host core, and there are several clusters containing RISC-V 32 cores and the SPUs. And well, because it's an FPGA, that's a programmable hardware, it contains our hardware architecture, and so this is really, really close to the finally produced chip, of course. So lots of complexity in our project, to be honest, was caused by the multitude of usage scenarios, because you have combinatorial explosion of of things you need to do. Do you want to build dynamic or shared or static executables? Are you targeting x86 or RISC-V 64 or 32 or the SPU simulated, very-related, and so on? So it's like lots of development efforts have gone into supporting all of this. Okay, so let's talk a bit about LLVM's OpenMP offloading implementation before going into details later. So if you execute the example program I've already shown you, what you see on the right is, you see that on the host, my value is set to 1, and correspondingly 1 is printed. If you map this variable by OpenMP data mapping to the device at entry, it's still 1. Then the device sets it to 2, and then the data is mapped back to the host, and in the end, the host also prints 2 here. And I mean, if you think a bit deeper about this, there seems to be some magic going on, because I mean, it looks very simple, but it's simple because there's lots of compiler infrastructure that enables this simplicity. Because the variable, my value, which is set to 2 here on the accelerator, I mean, this is a value, for example, in memory of an accelerator, and that's not in the host RAM, maybe. So you need to have, for example, the context switch between the host and the device, including the data mapping of variables to and from the device, be done in an automatic way, so you don't need to care about it. And of course, you need to generate binary code not only for the host, where you start your final executable, but also for your device. And all of this has to happen in a single call of clang ++ minus f OpenMP target equals and so on. So there's lots of stuff going on here behind the scenes. And let's talk a bit, how this actually works. Well, I mean, first, if you compile an offloading binary with Clang, you do something like clang ++, you activate OpenMP, and then you say minus f OpenMP targets equals, in our case, SPU, STX, unknown elf as a triple to identify the target architecture, and then, file.cpp, and what you get in the end is your offloading binary for the host. Well, first, a simplified view of the general non-offloading compilation process is you start on the left-hand side with your C++ file, you put it into Clang, that's the C++ front end for LLVM, and it generates LLVM intermediate representation. That's some kind of assembly language that is target agnostic, it's reduced to the basic concepts of what like each architecture should have: registers in an unlimited amount, moving data, doing address calculations, adding, multiplying, and so on. And then in the LLVM middle end, there are lots of target-independent optimizations on this IR already going on to, for example, simplify this IR, roll out loops, and so on. And after you're finished with your target-independent optimizations, you go into the LLVM backend and create binary code for your specific processor architecture. Then you link everything with ideally the LLD linker, the linker provided by LLVM, and then you get your final binary. So that's the basic way of how a C++ file is turned into binary code by LLVM. And lots of passes are running in the middle and back end to do the actual work. And yeah, if you want to support a target like this, you need to write passes that do the optimizations and generate the binary code, and so on. So now in a bit more detail about OpenMP offloading compilation. Because in the end, as you can see, if you activate via the save temps flag, this saving of intermediate artifacts, in the end you get a binary file called test in this case, but you get lots of other stuff here. Because for the host, as I said, you need to generate binary code. You need to generate binary code also for the device. The host in this case is x86. The target architecture for the device is our SBU in this case. And what you get is like from the source file, II is preprocessor output. Then you create a bitcode or LLVM IR for this. And then you get assembly.s, and then you get an object file .o, and this is linked in the case of the offload target to a so-called device image. In this case, it's called test.sbu.native.image. And that's a linked image with the binary code for the device you want to offload to. And this image is injected into the host binary. So in the host binary, which is in the ELF file format, there's not only code for the host binary code, but there's also the device image for each accelerator you want to offload to. And at runtime, you need to handle this device image to offload, to do the actual offloading. And how do you instrument all of this? Well, in Clang, there's something like, it's called the OpenMP driver. It orchestrates all the necessary compile, assemble, link, and special offloading actions you need to do to get, in the end, get down here via the Clang linker wrapper, the final fed binary for the host. I don't want to go into the details here, but as you see, the test.cpp input goes into preprocessor, and then it's IR is generated for the host, but the same is done also for the device, and then everything is processed through this tree. And lots of flags need to be set correctly in doing this, especially since this is not the full truth, but this is called actions. But there's also a concept of jobs, and the jobs are the actual command line calls that are made to call programs that really do this. This is also a bit different, and yeah, it's the OpenMP driver alone is complex by now, and it knows how to do this for you. Well, and all this is done automatically behind the scenes when you do clang ++ minus f OpenMP targets equals, and that's why it's for user it's convenient, because you get a single fed host binary and simply start it and get your single source file approach. Okay, so how is OpenMP offloading at runtime done in LLVM? As I said, if you execute this program, you get the output on the right-hand side, which means it works. For example, the data mapping of the myValue variable works correctly. But you do not see any explicit code here that calls an offloading library or does any special things. So how does it happen at runtime? So if you activate debug output of the offloading runtime library, you get the output on the right. And from top to bottom, you see host 1, device at entry 1, device at exit 2, host 2. That's the actual output of your program. But in between, there's lots of stuff going on. even before main is entered on the host, at the very top, you will see init target library, and then loading dynamic RTLs. That's the target independent offload runtime library in LLVM, libom target, loading all the plugins for offloading to the available accelerators. And you also see output of something like registering image just above host 1. That's where the device image for the accelerator was found and is associated to the corresponding plugin. And then main is started. Well, the host 1 output is done. And let's jump back. If you reach this OpenMP target map here, that's the place where you enter the target region, and there you see entering target region for device, and there's some data mapping going on here. You can see how the my value variable is mapped to the device, and then you finally see the execution of the device code here. When leaving the target region, data is mapped back to host. You are back in main, output host, and then some cleanup is done by deinitializing the offload runtime library, and that's what happens behind the scenes. And if you wonder how this is done, well, yeah, I will show you in a minute. This is done by features done at compile time again. Because, yeah, you may ask yourself, what happens at compile time to achieve the described runtime behavior? Who calls the initialization of the libom target runtime library, for example? There's nothing visible here in the source code. Yeah, for example, if you look at code for the device, this is LLVM IR. That's the intermediate representation, a part of it for the device, for the SPU in this case. And what you see here is the result of OpenMP code generation. That's something that's instrumented by the Clang frontend. It takes the source file and it generates IR for it. And as you can see, there's a method, or a function better. It's called OpenMP Offloading, blah, 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 main line 8. And that's exactly the identifier of the target region with the source code for the device. And what you see is the variable my value in source code has been turned into a parameter of this function. Yeah, and that's basically the concept of outlining the target region to an outlined function. And that's why you can well, create binary code for this function by the normal LLVM mechanisms and have this binary code in the end. So what, and also you see so-called OpenMP offloading entries, and an offloading entry is like, yeah, let's call it an identifier in the object file, which says, yeah, for each target region that needs to be offloaded to the device, you have an offload entry that says, the target region has this name and its function sits there and so on. So all of this has to be injected into the device code, and in the end ends up in the device image. And on the host, if you look at the host code, there's also OpenMP code generation going on for the host. What you see here is the main function on the host, and you also see, where is it? Store 1 into my value, into this pointer. That's the code line where the user wrote my value equals 1. And all of the rest is generated. And what you see here is the data mapped variables are in the end placed in these kernel arcs. And these kernel arcs, it starts at the very top. Offload base pointers, allocar 1 times pointer. It's an array of pointers, and each variable that is data mapped to the device from the host becomes an argument of this outline function, as I've shown you. And then you put all those, this code puts all the pointers in an array and hands them to the offloading runtime library by calling target kernel. And that's how, in the end, the device code is executed. And that's why it works. That's the basic idea behind OpenMP offloading in LLVM. Okay, besides this shown OpenMP code generation, there's lots of other things going on. You need, for example, of course, a plugin to offload to your specific architecture and so on. And due to the special STX architecture we have, as I mentioned, there were lots of challenges. Support a specialized instruction set architecture processor in LLVM, support 2-level nested offloading, offloading from bare metal targets. And well, there's was a need for implementing really lots of functionality in SBU LLVM and surrounding infrastructure to get this working. So let's show some of the things we developed. First of all, what you need to do if you want to support a target like ours, you need to have an LLVM backend for, in this case, SBU binary code generation. Then we have a software simulator for the SBU, a driver for the stencil processing unit in different flavors, depending on whether you want to offload to a simulator or hardware or very later version. Then we developed an offload plugin for offloading to the SBU. That's the OpenMP Offload plugin that talks to this driver. Then we need a minimal runtime library for our bare metal clusters, providing some minimal memory management functionality, for example, for the RISC-V 32 cores. For offloading from our bare metal RISC-V 32 clusters, we needed to implement static build support for libom target and the plugins, because normally in upstream LLVM project, the offload runtime library, libom target and the plugins, the offload runtime library loads the plugins dynamically. We don't have this available on the bare metal clusters, so we needed support for fully static binaries. Then we needed support for libom target on 32-bit systems, which is excluded at the moment in upstream, I think. Support for libom target on RISC-V 32 as host. Support for libom target on bare metal systems, because you don't have really have an operating system. You have reduced C library support, no threading, no atomics in the case of RISC-V 32, no dynamic linking. So there was really lots of efforts going into this to simply get this working in the first place. Then, because of this bare metal approach, we do not have ELF object file support. We do not have a libelf for reading ELF files. Nowadays in upstream LLVM, I think since my last upstream merge in May, the ELF handling is changed in libom target. I think there's self-contained ELF image handling in LLVM project. Sorry, but if I remember correctly, this also assumes some kind of operating system support. No, I take back what I said. I think this still wouldn't work with upstream LLVM project. So we don't have ELF library support, and what we ended up with was process parts of the generated device image at compile time on our host machine, and then inject annotations in the form of metadata into the device image, so that on a bare metal system you can read the device image in the end without having such support. Second slide. Since we are offloading from RISC-V 62 to RISC-V 35, what you typically do is with LLVM, you do not take the libc or libc++ from LLVM itself, but in the case of RISC-V, for example, you simply use GCC toolchains, which provide the dependencies for you. libc, libc++, and so on. But in our case, we have two offload. We have a host RISC-V target and a device RISC-V target, and we needed to implement flexible handling of target flags for host and device for specifying two different target-specific GCC toolchains providing dependencies. So that's also something we needed to change. We needed very fine control over compile and link flags during offload compilation. We needed to implement nested OpenMP offloading in libom target and the plugins. Implement Linux kernel module as a driver for the X cluster for RISC-V 64. Of course, an offload plugin for our RISC-V 64 host core to the RISC-V 32 clusters. And because we are offloading from a single RISC-V 64 host core to many RISC-V 32 clusters, we did this in a way where the plugin on the RISC-V 64 host simply places an offload request to a mailbox, which all the clusters can observe. So on the clusters, there are already offload managers waiting for offload requests to make this efficient. Of course, we needed to change the OpenMP driver in Clang for the special linker flags handling for the STX and the Clang linker wrapper. So really, as you can see, lots of work went into making this work. Okay, and now at the end, I want to show you as an example two special challenges we were facing and how we were solving it. Okay. So, as I said, STX's stencil processing unit has a specialized instruction set with, for example, hardware loop generators to iterate over center points in the data volumes. You have something called resource identifiers, which specify the data layout in memory. You have special load store instructions depending on the above. And the general mechanisms in LLVM for address calculations and data movement in LLVM IR are not made for this. They are made for general purpose targets. So these things in the target architecture for the SPU cannot be directly expressed in LLVM IR. But nevertheless, we need to generate binary code for it and offload to it automatically at runtime. And the solution we went for was by using dedicated SPU passes, we replace standard address calculations and data movement in IR by intrinsic functions plus metadata. These intrinsic functions are like placeholder functions that will be lowered to actual binary code in the end because our backend knows how to do this. And the metadata is metadata about data movements and address calculations, which is used at runtime by the offload plugin to do the actual computation configuration of the SPU when all the state information about the host is available. So the metadata is added to the SPU's device image. And at runtime, the OpenMP Offload plugin takes the binary code and the metadata and the information about the program state of the host, including the data layout in memory, and then configures and starts the SPU accordingly, the instruction memories, loop generators, resource identifiers, and so on. So that's why it works. So in a simplified form, for each target region on the left, you get an offload entry in the device image, and the offload entry contains binary code for something called SAG and AU in our architecture, and also the metadata, for example, on runtime RID configuration. And if you compile the left example program here, targeting the SPU and activate debug output during IR generation, on the right-hand side, you see metadata that is generated for the target region on the left. As you see, we have my effector, minx, and maxx mapped to the device via pragma OMP target. For example, minx and maxx are minimum and maximum bounds for that loop. And on the right-hand side, I hope you can see, it's a bit hard to see. You see metadata for example, SPU program loop info. It says we have the arithmetic unit with, for example, start and end index is data mapped from argument index 0 and 1, and below there you see index 1 and 0 and 1 are in 32 values. So this is the metadata that tells the plugin at runtime that some loop generators have to be configured using data map values arriving from the host. And that's the basic idea how the offload plugin can configure this. And correspondingly, if you execute this program, that's again the libom target debug output. You see target RTL launch kernel, and that's the offload plugin for the SPU. And the plugin says, the offload function is in the OpenMP programming model. I'm configuring the resource identifiers, some registers, loop generators, and so on. And I'm starting 2 SPUs because there also was a work sharing hint. I've shown it here. It says pragma STX work sharing because we want to automatically do some kind of interleaving work sharing for 2 SPUs here. So the plugin can automatically determine this based on the metadata and do the computation accordingly. That's how we implemented support for a specialized instruction set architecture in OpenMP Offloading for in LLVM. And the second thing I want to show you is nested OpenMP Offloading. As I mentioned, we have nested or 2-level OpenMP Offloading for the STX. You offload from the host to, which will be RISC-V 64 in the end, to a first-level device, which will be RISC-V 32, and then offload to the stencil processing unit. And you need to get lots of things technically correct in LLVM to make this work. You need to have correct OpenMP code generation for nested target regions. You need to generate offload entries for device images of 2 targets in the fed host binary. You have 2 libom target instances at runtime on host and device level 1. The offload plugin for device level 1 needs to manage the libom target on the device. Also, the binary code from the fed binary has to be loaded correctly and distributed to the correct libom target instances. So lots of changes here that we needed to do. And instead of going into more slides or technical details, I'm doing a demonstration of this. I'm going to debug into the execution of a simple test program. I'm doing this on my machine, x86, to x86 to simulated SPU offload, because of course I can demonstrate it more easily than in QEMU, for example, here. Okay, let's go to, this program, and I'm going to start it. And I will talk about what it does while it is running. So I've set some breakpoints here for execution, and what you immediately see is in the call stack we are still in libc start main. So the C library is still doing the work for starting the main function. Main has not even started, and we are doing init target library here, and that's the initialization of the libom target library. You see on the down here that the plugins have been loaded, and the fact that this code is executed comes from OpenMP code generation. There has some constructor code been injected into the host IR, which then calls this functionality. Okay, so now we are starting main, and we are creating 2 clusters here with simulated SPUs. And let's continue here. What we are doing now is we are preparing some data volume on the host. In this case, it's very simple. It's 1, 2, 3, 4, 5, 6, 7, 8 with some host values, and the goal is to double all these values using 2 clusters and the SPUs inside the cluster. So let's continue here. For this simple example, I've set the number of clusters to 1 because otherwise there's too much going on here in the debugger. But you could change the value to another value here. So now we want to do the offload to the first level device. We are reaching OpenMP target teams. Let's continue here. And now you can see we are in the libom target runtime library. Target kernel has been reached, and we want to start the code on device level 1. Let's continue here. The library is initialized. And at this point, the device image is loaded from the host binary. Let's continue here. And then we are, sorry for the jumping, in the plugin. As you can see on the top right, it's generic ELF 64-bit. That's the place where the binary code from the device image is loaded. That's intended for device level 1. This will take a minute because it's loaded at this point in time. And what you see now is we are again in init target library. And that's the initialization of the device level 1 libom target instance, because corresponding code has been injected, and after this device code is loaded by the plugin, this needs to be initialized. So let's initialize it. What you see now is, the output here running host libom target, checking whether device supports nested offloading. Yes, the device supports nested offloading. So what we do is initialize the device libom target here. And now we are in target RTL launch kernel. We are ready to actually start the device code on device level 1. Let's wait a minute. Okay, so now we are on device level 1 here. What you do here is you determine based on, for example, let's continue here. In this case, we only have the cluster with index 0, and the chunk size is 8 here, because we only have 1 cluster here. Now we copy data from host RAM to the cluster scratchpad memory and continue. And now we are reaching the point where the second level offload is happening to the stencil processing unit. Let's continue. You see we are again in libom target, but now the libom target on device level 1. We are entering the target region. We are again initializing the library. We load the device image, in this case the device image for the SPU. We load the corresponding binary code in the SPU's offload plugin. And now we can launch the device SPU target region. We cannot debug into this because it's not a general purpose processor, so let's simply continue. Now the target region for the SPU has finished. We are back on the host. Copy the data back to the host. No, sorry, we are sorry, we were on device level 1 and copy the data back to host, and now we are back on the host. And now I hope you can see in the end that, yeah, it worked on the host. In the end, you have 2, 4, 6, 8, and so on. Everything has been doubled by, yeah, using a nested OpenMP offloading approach. In the end, letting the SBUs doing their work. Maybe let's get back to the slides one time, because I have to thank you for your attention. And that's all I wanted to tell you today. For those, this wasn't enough to digest, we bring in the pizza and questions. Great idea.